Welcome back, everyone. In this lesson, we're going to be starting Chapter 19, which is an introduction to the chemistry of aldehydes and ketones. While we will be covering most of the sections in Chapter 19, there are several that I want you to read about because they are good introductions to the material that we'll be covering in these videos. So for example, for Section 19-1, which is about the nomenclature of aldehydes and ketones, I'd like you to read that in the textbook. And also, I would like you to read Section 19-4, which is a good introduction to the video lessons that will follow that section. So with that, let's go ahead and get started learning about aldehydes and ketones. And we're going to start here in 19-2, which is about the reactions that we can use to prepare both aldehydes and ketones. The most straightforward method that we have for preparing aldehydes is by oxidation of primary alcohols. As we learned in our study of alcohols, we found that it was necessary to use selective oxidants in order to oxidize primary alcohols and stop at the aldehyde stage. Specifically, we learned about two different selective oxidants. The first of those was pyridinium chlorochromate, or PCC. Treating a primary alcohol with PCC prepares the aldehyde. The other selective oxidant that we learned about is called Des-Martin's periodinane. Using DMP, we can also oxidize primary alcohols to aldehydes. So oxidation of primary alcohols to aldehydes is definitely one very nice method that we have available. However, we have learned a few other oxidation-type reactions that will lead to aldehydes. For example, we learned how to convert terminal alkynes into aldehydes last semester when we learned about hydroboration oxidation. When applied to a terminal alkyne, hydroboration oxidation also allows us to form an aldehyde. We learned that this is possible because hydroboration oxidation produces an anti-Markovnikov alcohol. However, in the case of a terminal alkyne, it's not just any alcohol, it's an enol, and enol tautomerizes to the aldehyde when the reaction is complete. So hydroboration oxidation of terminal alkynes is another very nice route that we have available to make aldehydes. We also learned that it's possible to conduct oxidative cleavage reactions to produce aldehydes. For example, ozonolysis of an alkene under reductive conditions produces an aldehyde, or we can use the Johnson-Lemieux oxidation of 1,2-diols also to produce aldehydes. There's one additional method that I want to show you for making aldehydes, and it's actually not an oxidation, but rather a reduction. It turns out there's a reagent that will let us, in most cases, reduce esters to aldehydes, and this reagent is called dibol, or dibol-H, or in some sources like your textbook, dibol. It stands for diisobutyl aluminum hydride, and it's similar to the other hydride reagents we've looked at, like sodium borohydride and lithium aluminum hydride, but it's very sterically hindered around the aluminum. What that means for you is it's possible to reduce esters to aldehydes using this reagent at very cold temperatures. We usually see this run at negative 78 degrees Celsius, and following an aqueous workup, the aldehyde is isolated. So that's a brief review of the functional group interconversions that we have available to prepare aldehydes. When these functional group interconversions are also coupled with the carbon-carbon bond-forming reactions that we already know about, such as alkyne alkylations and Grignard reactions, they provide us a lot of opportunity to make exactly the kind of aldehyde that we might need in a synthesis reaction. Towards the end of the lesson, we'll take a look at a few of those types of examples. For now, let's go to the next part of this lesson, which is about preparing ketones. Methods that we have available for preparing ketones largely parallel those methods that we have for preparing aldehydes. For example, we can also oxidize alcohols to ketones. However, instead of using primary alcohols like we would for aldehydes, we use secondary alcohols when we're trying to make a ketone. For ketones, we don't need to worry about using selective oxidants, so we can use anything ranging from PCC or Des-Martin's periodinane all the way up to the chromium-6-based reagents like chromium trioxide or the Jones oxidation conditions. Also similar to aldehydes, some ketones can also be prepared from terminal alkynes. Specifically, we can convert terminal alkynes into methyl ketones, but instead of using hydroboration oxidation, which would give aldehydes, we have to use oxymercuration type conditions. Specifically, the conditions that we use to convert terminal alkynes into methyl ketones use water, a catalytic amount of sulfuric acid, and mercury 2 sulfate. This reaction, which we covered in Chapter 9, also goes through an enol, except with this particular enol, we're doing a Markovnikov hydration. So the hydroxy group that's added when we hydrate that alkyne goes on the more substituted carbon atom rather than the less substituted carbon atom that we would see with hydroboration oxidation conditions. The result of this, of course, is that we make a ketone because we're putting that hydroxy group on the more substituted carbon atom. One helpful way to remember this is by looking at a ketone as fundamentally Markovnikov and an aldehyde as fundamentally anti-Markovnikov. You can see this by looking at the placement of the oxygen atom of the carbonyl group in each functional group. If we take a look at aldehydes, we see that the oxygen atom is attached here at carbon 2. In the ketone, however, the oxygen is attached at carbon 1. It has two R groups on either side. That makes the ketone, naturally, this carbon of the ketone, a secondary oxidation. That we could say is Markovnikov. Remember, Markovnikov's rule is that the heteroatom, like oxygen or bromine, goes to the more substituted carbon atom. So here we see the heteroatom, which is oxygen, on the more substituted carbon atom. So naturally, ketones are Markovnikov. If we compare that with aldehydes, we see that the heteroatom, which is oxygen, is on the less substituted carbon atom. This is only a primary carbon atom because we have to have an H on one side of an aldehyde and an R group on the other. This means that aldehydes are naturally an anti-Markovnikov oxidation because we have the oxygen on the less substituted carbon atom. So that's another way that we can prepare ketones, specifically methyl ketones. We can convert a terminal alkyne into those functional groups by using oxymercuration type conditions. Now, what about some other methods to make ketones? Ozonolysis can also be used to prepare ketones, provided we're starting with an alkene that's substituted in such a way as a ketone would result. Necessarily, this requires at least a di-substituted alkene in order to make a ketone because of the two R groups on either side of the carbonyl carbon. And of course, we can also use the Johnson-Lemieux conditions to oxidize 1,2-diols to the corresponding ketone. We also learned a few carbon-carbon bond-forming reactions that prepare ketones. For example, the Friedel-Crafts acylation lets us prepare aromatic ketones, and we can also use the Grignard reaction in combination with our oxidation reactions to prepare ketones as well. To use this method to prepare ketones, we need to remember that the precursor to a ketone is a secondary alcohol, at least if we're talking about doing oxidation reactions to make ketones. So if we want to make a ketone this way, we need to use our Grignard alcohol synthesis specifically to prepare secondary alcohols. What that means is the carbonyl compound that we're doing the Grignard reaction with needs to be an aldehyde, because a Grignard reagent plus an aldehyde makes a secondary alcohol. If we used a ketone as our carbonyl compound, we would make tertiary alcohols which can't be oxidized to ketones. So if we want to make a ketone through the two-step Grignard procedure, we take our Grignard reagent, we react it with an aldehyde to make a secondary alcohol, and then we oxidize that secondary alcohol to the ketone. As we learned while we were studying the chemistry of alcohols, aldehydes can be oxidized to form carboxylic acids. This is because of the presence of a hydrogen atom at the carbon atom which can be oxidized. Notice, however, that ketones don't have a hydrogen at this location. This is why ketones are not oxidized to carboxylic acids like aldehydes are. This is why ketones are generally inert to oxidizing conditions. However, there are some that will allow reactions like an oxidative cleavage. For example, when a ketone is boiled in potassium permanganate with a base present, it undergoes an oxidative cleavage, leading to a dicarboxylic acid. In general, however, we don't often see oxidations of ketones, whereas we do often see oxidations for aldehydes. So now we've completed a review of the various methods that we have available for preparing aldehydes and ketones, as well as a few reactions of aldehydes and ketones. Now let's take a moment and go to the next page and put some of this together with some sort of simple synthesis problems that will allow us to review how these methods can work together. So a really good way to review all of this information is to look at problems that tie together multiple methods. These are often simple synthesis problems. So I have a few here. We're starting from an alcohol. This alcohol has 4 carbon atoms, and I want you to show the routes that we have available for converting that alcohol into this aldehyde. I have the same starting material down below, but in this case, I want you to come up with methods that show how we might convert it into this ketone. So go ahead and start with this first problem. Pause the video and see if you can design a route to convert this primary alcohol into this aldehyde. So hopefully you didn't forget to count the carbon atoms and notice that there are a different number of carbon atoms in the starting material than the product. The starting material has 1, 2, 3, 4 carbon atoms, but the product has 1, 2, 3, 4, 5 carbon atoms. That means you can't just do a simple oxidation, say with PCC or DMP, to convert the starting material into the product. Instead, you need to do a carbon-carbon bond forming reaction. Since we're only adding 1 carbon atom and converting it into an aldehyde, that means we're probably best suited by using the Grignard alcohol synthesis. So my first step in this method will convert the alcohol into the necessary alkyl halide. Once I have that alkyl halide, I can complete the Grignard alcohol synthesis using a carbonyl compound to give me a primary alcohol. I need a primary alcohol, of course, because I'm trying to make an aldehyde. Remember, it's the oxidation of primary alcohols that gives aldehydes. So now that you've seen this route, you might want to revise the one you have, or maybe you have exactly the same types of reactions that I've shown here. If so, great job. But if you didn't get this particular route, that's okay also. This is an excellent point to review the reagents that are necessary to do each of these conversions. So let's take a look at this first reaction where we're converting the primary alcohol into the alkyl halide. That's one of the methods that we learned about when we studied alcohols. Do you know what reagents we would use to do that? If not, you should pause the video and go look at your lesson note outline, or watch the video or read in the textbook to try to find out how you accomplish this kind of transformation, because it's essential. Without this kind of transformation, you won't be able to solve pretty much any of the synthesis problems that we'll be doing. While there are multiple methods available for converting primary alcohols into alkyl halides, if we want to make the primary alkyl bromide, probably the easiest way to do that would be using phosphorus tribromide. Once we have that primary alkyl halide, how do we convert that into the primary alcohol? Well, that's right, we need to use the Grignard alcohol synthesis. If you haven't already written down the reagents necessary to accomplish this specific transformation, this is a great opportunity for you to pause the video and see if you can learn more about the Grignard alcohol synthesis. Try to figure out what series of reagents you need to put together to accomplish this transformation. For the Grignard alcohol synthesis, we can either make primary, secondary, or tertiary alcohols. And whichever alcohol we're trying to make will basically determine the type of carbonyl compound that we're adding to the Grignard reagent. The first step in our Grignard alcohol synthesis, of course, is to form the Grignard reagent, and that requires us to add magnesium in dry diethyl ether. After that, we add the carbonyl compound and do an aqueous workup. Because we're making a primary alcohol in the Grignard alcohol synthesis, that means we need to use formaldehyde. So first we add magnesium turnings in dry diethyl ether, then we add formaldehyde, and then we do an aqueous workup. And in this way, we will form this particular primary alcohol. Now that we have the primary alcohol, it's a single final step for us to convert that into the aldehyde. And for that, we need to use a selective oxidizing reagent. We can choose to use PCC, which is pyridinium chlorochromate, or we can use the Des-Martens periodinane, or DMP. So over the course of 3 steps, we can convert this 4-carbon alcohol into this 5-carbon aldehyde. If you got that sequence correct, great job. Let's try the next example. In the second example, I have the same starting material, but I'm trying to make a ketone. Go ahead and pause the video and review your methods for making ketones. See if you can put together at least one route to do this conversion. Once you have one route planned out, see if you can come up with a second one. It's always a good idea when you're trying to review organic reactions to try to think of as many ways as possible to do the same thing. That way you can cover a lot of ground in a short amount of time. When you unpause the video, we'll go through the methods together. I'll show you 2 different ways to convert this primary alcohol into this ketone. As I've mentioned before, one of the best ways to become better at doing synthesis problems is to completely ignore the starting material and instead work backwards 1 step at a time from the product. So that's what I'm going to do over here in the margin. I'm going to focus all of my attention on trying to identify the precursors, that is, the molecules, that I could make this ketone from using only one reaction. So for example, one way that I know how to make ketones is by oxidizing secondary alcohols. So for example, maybe this ketone came from the oxidation of the secondary alcohol. But here's the thing, I always like to think of alternatives. Like, what if there was some other precursor that this ketone came from? So what I do is I scan my memory and try to think of all the other ways I know how to make ketones. Now I also notice this ketone is a methyl ketone, and because of that, I remember that there's another way to make ketones, specifically methyl ketones, and that is the oxymercuration-demercuration reaction of terminal alkynes. So maybe this ketone came from a terminal alkyne. So these are 2 immediate precursors of this ketone. Now I can tell you there are others as well, but I'm focusing on these 2 for this particular example. Now, if you came up with a different precursor, or maybe several other different precursors, that's great. See if you can do what I'm about to do with these precursors and get back to the starting material. Okay, so now that we have these 2 precursors, what do we do next? What we do next is exactly what we just did with this ketone. We try to imagine the direct precursor of these precursors, one reaction back at a time. So I have to try to think of a way to make secondary alcohols, and I also need to think of a way to make alkynes. Now, if I wanted to show all of the precursors for making secondary alcohols, I'd be here for quite some time. For example, we can make secondary alcohols from alkenes, we can also make them from alkyl halides, and we can make them using the Grignard alcohol synthesis. The synthesis of alkynes, however, is a little more limited in context. We really only have a few methods for making alkynes, the main one being alkyne alkylation. That's a carbon-carbon bond-forming reaction. So if I wanted to make an alkyne that way, I would need an alkyl halide and another alkyne that I deprotonated. So these would be the 2 precursors if I went down that road. Now let's go and try to find some other precursors. For example, how can I make alkenes? What's the immediate precursor to an alkene? Well, there are a lot of precursors to alkenes, but probably the easiest one to think of is a reduction of an alkyne. So for example, if I took a terminal alkyne and I reduced it, it's possible to stop at the alkene stage by using a Lindlar's catalyst. If I wanted to go down this road, I would have to think of an immediate precursor of this alkyne. This is that alkyne alkylation reaction again, which, if you notice, gives us exactly the same precursors as we saw over on this side of the synthesis. Let's say I didn't want to use terminal alkynes for some reason. I could maybe think about what are the precursors of this Grignard reaction. All I have to do is think, how would I make this Grignard reagent? The immediate precursor of a Grignard reagent is just an alkyl halide. So all I have to do is have the same molecule, just without magnesium. So let's take a step back for a moment and take a look at what we've done. Do you notice anything kind of funny about all of these retro syntheses? That's right, they all lead us back to one common precursor. That's a really nice situation to be in because it means if we can just make that precursor, we have at least 3 different ways to convert it into our desired product. The question is how do we actually make this alkyl halide? Let's see if we can go 1 step backwards and find the immediate precursor of this reagent. That's right, we can make it from a primary alcohol. Primary alcohols can be converted into primary alkyl bromides by using phosphorus tribromide. Notice that this alcohol matches our starting material. So if you think about what we just did here, going 1 step at a time backwards using reactions that we definitely know about, we can get back to our starting material. But I didn't even think about the starting material at all. I just went back one step at a time. One of the things that I can guarantee about synthesis problems in this class is I will give you a product where if you go back one step at a time using reactions that we know, not ones that you've made up or that you think could potentially work, but actually known reactions that are guaranteed to work, you will get back to the starting material in just a few steps. So now that we have these 3 different routes planned out, let me just show you the forward synthesis using one of them. And I'll pick the longest one and the one that I think is probably the most interesting and good for review. So specifically, I'm going to take us down this route where we start with our starting alcohol, of course, and then we're going to go back up this direction through this route. Now, it would be an excellent review for you to go through and make sure you know all of the reagents to do the other routes as well. So the first step in our forward synthesis is to convert this primary alcohol into the alkyl halide that I've circled in red here, and we would do that using phosphorus tribromide. Once we have that alkyl halide in hand, we need to do an alkyne alkylation reaction. Because we need to add 2 carbon atoms, we necessarily need to use the lithium salt of acetylene. Once we have this alkyne alkylation complete, we've made a terminal alkyne, and we already have the necessary number of carbon atoms in our chain to form the product through a series of functional group interconversions. The first functional group interconversion that we need to do is to convert this terminal alkyne into this alkene. We can do that by controlled hydrogenation. So we would treat it with H2, and we would use Lindlar's catalyst so that we could stop at the alkene stage. Once we have the alkene, we can now convert this into the secondary alcohol. This is a Markovnikov hydration of alkenes, so we would use oxymercuration, demercuration to accomplish this transformation. Now that we have the secondary alcohol, it's a simple matter to oxidize this to the ketone. You can use any number of oxidizing conditions that would convert secondary alcohols into ketones, such as Jones oxidation or PCC or Des-Martin's periodinane, but I'll go against the grain here and I'll use chromium trioxide in acetone. If you got that synthesis right, great job. I hope this is helping you learn a little bit more about how we can do retrosynthesis, and specifically how we can use retrosynthesis to our advantage in making problems that seem really complex much easier to do as long as we keep our view constrained to one reaction at a time. And with that, I'm going to end this lesson. I hope you're doing well. Please let me know if you have any questions, and I will see you soon. Take care.